All right, so let's talk about object-oriented programming. And the first thing that we should probably mention is that the cool kids aren't really out there promoting object-oriented programming. Most conferences like this, and because I work on conferences, I know what gets discussed at C++ conferences, and most of the cool kids are not promoting object-oriented programming. In fact, they're showing you alternatives to object-oriented programming, things that can be done at compile time as opposed to at runtime. And I know that this is true largely because, as I said, I know what people are talking about at conferences, but also because I'm one of the cool kids who are advocating alternatives for this. So in this talk, we're not going to be discussing, should you be doing object-oriented programming? What are the alternatives that we could be doing? That's not what we're going to talk about. What we're going to do is we're going to first cover kind of the theory of object-oriented programming, and then we're going to talk about some best practices. First, design level best practices, and then build level or code level best practices for how you write code using object-oriented programming. And I'm going to talk about the definition of object-oriented programming. And the reason this is important to do is because the term object-oriented programming sounds like it defines itself. You should be able to go up to somebody who knows nothing at all about programming and say, what does object-oriented programming mean? And they will say, well, it's programming oriented around objects, right? And that sounds like that should be the correct definition. But if you look in the literature and if you look in academia, that is not, in fact, the definition that is usually used for object-oriented programming. That would actually be a pretty good definition for what's called object-based programming. Object-oriented programming almost always is assumed to use some type of inheritance relationship and some kind of inheritance hierarchies. So the definition I'm going to use, and that's for this session, because specifically I'm going to be talking about C++, and of course, object-oriented programming can be done in almost any language. So, I'm going to say, define it for the purpose of this session as a programming paradigm in C++ using polymorphism based on runtime function dispatch using virtual functions. So that's what we're going to talk about, and that's what we're going to focus on for this talk. And there are, as I said earlier, there are a lot of alternatives, object-based programming, static polymorphism, functional programming. I'm not going to talk about any of those alternatives, and I'm not going to even talk about why you should be using object-oriented programming as opposed to something else. The assumption we're making is that you are using object-oriented programming. You've decided to do that. So our goal is that you do that in the best possible way. We're going to talk about best practices. And what I would say is that although this is not what we are talking about at most conferences today, you're talking about some of these alternatives. But, and I'm saying this totally without hard data to back this up, my guess is that of the 5 million people in the world that are doing professional C++ programming, the vast majority of them are working on code bases with a significant amount of object-oriented programming in them. And so we have this weird mismatch where we've done object-oriented programming for a very long time. In fact, C++ was kind of originally seen as an object-oriented version of C. And so it may be downplayed now when we think about templates and compile time programming now, but the original drive to use C++, which largely people wanting to do object-oriented programming. And so we have a lot of knowledge about how to do it right, lots of best practices stuff, but the people who are talking about C++ now are not talking about it. So we have this huge mismatch with a wide user base that needs to know best practices, because like any kind of paradigm, there are traps for object-oriented programming. There's best practices, and then there's things that people do naively. And so there are best practices to be taught, and it's not happening. So that's what this session is about. So I'm not going to get into any of the other things that we could argue about code. We're going to focus only on object-oriented programming best practices. So the first thing I want to do is talk a little bit about the theory of object-oriented programming. And I want to make the point that you can actually think of objects in an object-oriented programming world as if they were libraries. They all have the same API because they're all from this base class, and the base class lays out what the API is. But each individual object is going to have its own responses to calls against that API. For objects within a type, they're all going to have the same implementation because they're all going to have the same overloaded functions that we'll call. But individual objects actually can have different state because each object has its own unique state. And therefore, every individual object can be thought of, as I said, as a different library that's going to respond differently to the exact same API. So one of the powers of object-oriented programming is it allows us to create a separation of concern so that we have essentially 3 different kinds of code that can be optimized for solving specific points of view. So first of all, we have a base class, and that defines the API. And the example I have here is a very simple one, deliberately very simple, do logging. So it is the base class that defines what is the API of logging. What is it? How do we log something? And then in the derived classes, it is the responsibility of derived classes to figure out how you would implement that API. And of course, the designer of the base class is not ignorant of these kinds of decisions, but doesn't have to worry about any particular implementation. The derived class, though, thinks about, well, if I'm logging it, I could log it to a server, I could log it to the console, I could log it to a file. There's lots of different options. And then there's the client code. And the client code is what is going to use the API, call the API, and well-written client code doesn't need to know about what it's being logged to, but the client code understands what needs to be logged, when it needs to be logged, how often it needs to be logged. Those are the issues that the client code focuses on and doesn't need to worry about these other kinds of issues. So here's this example code where we have a base class that defines what the API for logging is. And it's very simple. As I said, I wanted to keep a very simple example. So we're just going to give it a C-style string, and we have implemented a particular derived class. This is the console logger, and it implements this log message call by writing to cout. Very straightforward here. But there is the separation of concerns. The base class defines the API, the derived class implements it. Now let's look at the calling code. So here we have a client. The client is going to instantiate a particular type of logging, in this case, our console logging. And then when we want to log something, we are going to call the API and log it. So the static type of the object we are making calls against is a base class pointer. So it's just the logger pointer. Now, in this case, because this is a very simple single function, we know that we're actually dealing with a console logger. But the power of object-oriented programming is that we're going to be able to write code against an API without needing to know what the actual type of the library of the derived class. We don't need to know what that is because we're going to write against the API of the base class. So the runtime type, the dynamic type, is actually a derived object, not the base class object. And so we have this is how object-oriented programming works. We have a base class pointer or reference, and we write code against that, but the actual object at runtime is a derived class and does an implementation that the calling code doesn't need to be concerned about. And that's the power of it. If we didn't use the virtual function, then we would actually be calling the logger's log message, the base class log message, because that's what we're saying to do here. If you look at this code, we are saying that we are calling log message on log pointer, and what's the type of log pointer? It's logger. So we should be calling logger log message. That's what would happen. But the magic of virtual functions is that if there is an overridden function in a derived class, then we will get that implementation instead. So now what we're going to do is actually do what I would call here, my term for this is a pure client. This client code here, log world, it does not know which kind of logger we're using. So main, of course, is actually instantiated in a console logger. So main does know that this is a console logger. But we're going to call log world, and we're going to pass in this logger, what is the type of logger? It's auto. So it's what are we getting here? It is a unique pointer to console logger. So when we dereference that, we are actually passing in a console logger that is taking a reference to a console logger, not a logger. and it's going to print hello world because that's what's going to happen. But in this case, we've actually cast that back down. So what are we passing here? Are we passing a console logger? No. The type that we're passing here is we're casting this to a logger and dereferencing it. So here we're actually passing the base class, but we're getting the same behavior. And that's the key to what's going on. This is pure. It gets the exact, the correct behavior regardless of what type is passed in. And that's the power of object-oriented programming, that we can write client code without being concerned what the actual object is doing. So here's another possible implementation. It's a file logger in its constructor. We're going to take the file name. It's going to make that. It's going to create a stream, and then the log message is implemented by writing to that stream. So now when in main, we can make both a console logger and a file logger and pass both of those objects into our pure client logger, log world, log hello world, and it behaves properly in both cases. And the log hello world has no knowledge of the actual type. So that's what we're trying to achieve with object-oriented programming. And the pure client is just written to the API and doesn't care what the actual types, the runtime types are passed in, and it just performs correctly. All right, so there's other possible implementations we could have, a dialog box logger, a socket logger, all sorts of things. I want to talk a little bit about Barbara Liskov. She defined something that she called the subtype requirement. And what she said is, for any type B, any base type, we have another type that's D that is a subtype of B. It is a proper subtype if all the properties of B are also properties of D. In other words, everything you can do with a B, you can also do with a D, then D is a subtype of that. In practice, this is interpreted to mean that the code written to behave correctly against the API defined by B will work correctly against D, then D is a proper subtype. But I want to point out that not all derived types are necessarily subtypes. Syntactically, you can make a derived type and it's not a subtype. So here's what we have here. I call it surprise logger. Surprise logger is perfectly correct C++. We are deriving from logger. We are overriding virtual function. But what are we doing within the function? Well, we're terminating. So this isn't really following the semantics that we expect of a logger, which is that when you call the function, it returns. So this is not a valid subtype. You cannot write valid code against the base class logger and then expect that this surprise logger is going to work. So the point we're making here is that when we're writing code, our goal is to write proper subtypes. And as designers, our assumption is that we are always dealing with proper subtypes. If you aren't dealing with proper subtypes, you can't really think logically and you can't make object-oriented programming work. You're going to end up with kind of this unmaintainable mess. So that's not what we want to do. So the idea is that we're understanding both the syntax and the semantics of the base class, and we're writing code that properly reflects that. So I'm going to be making a number of references to classic books that have been published for a very long time. And here we have, as you can see the little picture there, this is from C++ Coding Standards by Herb Sutter and Andrei Alexandrescu. And what they said is in Rule 38 in the C++ Coding Standards, after the base class guarantees the preconditions and postconditions of an operation, any derived class must respect those guarantees. An override can ask for less and provide more, but it must never require more or promise less, because that would break the contract that was promised by calling code. So I'm just setting up and saying this is the requirements that make object-oriented programming work, that we define a base class that defines an API, defines a semantic, and then we have derived classes that provide implementations that follow both the syntax, but just as importantly, follow the semantics, the meaning, the expectation, because that allows clients to write code against the base class and have it work properly, regardless of what the actual implementation at runtime turns out to be. So how does all this magic work? How is it possible that we can have a base class write code against a base class object, but then at runtime, It doesn't do what the base class do. Instead, it does the derived class. How can we make this work? Well, how do we solve any problem in computer science? We've got a level of indirection. So we have this keyword called virtual, and every function that's intended to be able to be overridable, any function that's intended to have this polymorphic behavior, is declared with this keyword virtual. Now, one of the implications of this is that what that means is that we can only add this polymorphic behavior to code where this is planned. In other words, the author of the code is going to decide in advance, this is a customization point. This function is overridable, because without the virtual keyword, we won't be able to do override. Then we have the objects of types that have this overridable feature all have a pointer to a table, which is called a v-table. Now, the v-table is not spelled out in the standard. It doesn't say how it works. It doesn't even say, theoretically, you don't even need a v-table. But in practice, that's how this is going to be implemented. So let's take a little bit of a look at that. So for every object of any type that has a virtual function or is derived from a type that has a virtual function, that object is going to have this pointer to a v-table as one of its data members. And within the v-table is going to contain addresses, all the implementations for those functions that have been designated as virtual. So the order of this is determined by the compiler. It's not really relevant to us. The function implementations are the same for all objects of a given class. So there's one v-table per class. The compiler is responsible for pulling together all of the actual implementation for a particular class. What is the correct set of implementations for all of the object of a particular class? So this is how this could be laid out in memory. Again, this is all completely up to implementations about how they want to do it. But this is a very straightforward approach to what could be done. So we have a pointer to an object that is that has this overridable behavior. And so the pointer is generally in object-oriented programming. We always have a pointer or reference of the base class pointing to the object. So in this case, we're pointing to an object. It has in it this v-table pointer, and it also has base class data members. And if it is derived, and in general it will be, then it may or may not have data members defined in that class. And if it is, then the data members for that will be in the memory. So this is the memory layout. Now, the v-table then, the pointer to the v-table is pointing to a table that is nothing but a set of function pointers. Now, the order in which these function pointers are listed in the table, again, completely up to the implementation, but you can imagine that the order in which the functions are defined in the base class is probably the order in which they are laid out in the v-table. So the first virtual function that's defined in the base class is going to be in position 0 and so forth. And then these are actually going to point to code, either the base class definition if this function has never been overridden, or the appropriate overridden function if if the function has been overridden. So that's what this is going to look like. And so this pointer that is called when we call these functions, they're going to have a this pointer, and that's going to be pointing back to this object here. And again, I want to emphasize, for a given type, there's one v-table for any given type that you've defined in your code base. And so there's going to be a single v-table for that. And it is up to the runtime when it instantiates objects to point to the right v-table. So we make an object of type foo, then it has to have a v-table a pointer to that v-table. If it's a derived object of foo, if it's actually a bar, then we have to get the right v-table, the derived object v-table. So this, by the way, is what what we are seeing whenever we pass in a base class object or a base class pointer to a base class object or a reference to it. The compiler is assuming that it's an object that has all the base class data members, including this v-table pointer. it does not assume that it is a derived object, because the static type of what we're dealing with is pointer to base class or reference to base class. So this is what the compiler sees for any function that gets a parameter passed in of a base class pointer or reference. So how is this actually implemented then? When a virtual member function is invoked on an object, the compiler is going to generate code to call the function whose address is found in the object's vtable. So we're going to call a function, and generally when generating code, the compiler says, linker, call the function with this name, and the linker provides that address. But in this case, what we're actually doing is we're going to write code that instead of just calling a particular function, it's going to say, oh, we're going to look in this object's vtable, look up the pointer to the function, and call that function. So it's determined then at runtime what the actual function is. So what does that mean? One of the implications of there is there's a little bit of dispatch overhead. It turns out to be pretty efficient, but there's a little bit. And that, by the way, does impact inlining. So it can have performance implications. And what do you think? Again, all objects of a particular type are going to use that same vtable. So if the compiler happens to know the actual type of an object, not just a base class, if the compiler knows this, or if the linker knows this, and sometimes with linker optimization or whole program optimization, it is possible for the tools to deduce, oh, in this particular situation, although it looks like we're passing a base class pointer, it is always a pointer to an object of a particular class. And then it may be that we don't actually have to do the virtual lookup because it can be done at compile time instead of runtime. But that is not the common case, but it is possible. So what we're going to do now is we're going to look at what actually is happening. So in this case, when we compile this log hello world function, the compiler is going to generate the exact same code, which you would expect. Here's code, it's going to generate code. But this code is going to do different things depending on the type passed in. So what is the code going to do? Well, what it's going to do is it's going to say, oh, you're passing in a pointer to a base class. That base class has a vtable pointer in it. I'm going to look in the vtable pointer, and I'm going to look at the offset, which in this case, the vtable is only going to have the only interesting function is a destructor, but the only interesting function is the log message. So it's going to look in there, and it's going to call the log message associated with this object. And it's going to get different behavior, although the code compiled here is the exact same code. So the generated calling code is the same no matter what the runtime type is, but the called code actually depends on that runtime type. Okay, so that is the behavior of the theory and implementation of object-oriented programming. I went a little bit fast, but I think that's because I think most of us are pretty familiar, but it is it's necessary to understand because we're going to build on this now. So the first thing I'm going to talk about are some guidelines related to design, and then we'll talk about some guidelines for coding. So the first thing I want to talk about and point out is that this is based on inheritance. And initially, a lot of people were attracted to inheritance because they said, oh, wow, we can use this anytime we have code that is similar. So we have this, these two pieces of code, and they're very, very similar. There's a little bit of difference between them. So we can have the code introduce this inheritance as a way of introducing variability in our code. And this is what a lot of people tried to do. It's attractive, but it turns out that if that's what you're trying to do, if you're just trying to reuse code and use inheritance to reduce your code duplication, that generally is not terribly successful. That's not the way to think about it. It's not the way to approach it. It's not the best way. The way to approach it is to think about object-oriented programming as a solution involving an inheritance model that is the inheritance model. So we make a base class that defines some generic type, and then we have derived classes which provide implementations that we can say this is a instance of the generic type. So we have the base class defining what the generic type is and what its API is, and then we have derived classes that implement those derived types, or that type for specific different types. So again, this is a contrary example. In this situation, what we have is, here's our base class for logging. Now we've made an object, and this object obeys the syntax that we've established for our logger. It just logs a message. But notice what it's doing. It's not logging, it's displaying status. The purpose of this logger is to show us what is actually happening right now. It's displaying status. But notice, that might be interesting, but that's not exactly what logging is. Logging is designed to show, after the fact, a set of interesting events that happened and they were logged. That's not necessarily the same thing as showing the current status. In other words, if I log that I've opened a file and I display that, it might imply that that file is still open, but maybe the file has already been closed. So displaying the current status is not the same thing as logging. And the reason I point this out is because if you think about this now from the point of view of the client, if the client's writing code to do logging, they're going to write code one way. But if they're ever thinking about, well, wait a minute, what if somebody makes something to display the current status instead of doing logging? And whatever the last log message is, that gets displayed as if that's the current status. Well, perhaps the log was constructed in a way that maybe we write out, we're saying something, oh, we're about to open a file, and then the next log message is the name of the file. Well, then for a period of time, the name of the file is the current status display, and it doesn't make any sense. So it might affect how clients try to write code. You see, there's an issue here. We have defined an API and an instance. We say, this is for logging, this is how you use it. And then we turn around and abuse that by saying, well, we can also use that to display the current status. And that's not the same thing. And that's going to confuse clients, and they won't know, well, am I trying to write code for logging, or am I trying to write code for displaying status? So again, this is falling apart because someone said, oh, look, we can reuse the code here. But it's not appropriate reuse because it's not following the idea of is a inheritance. Because this displayer is not strictly a logger. Even though the API works, code will work, the code will build, it will all be fine, but it's not doing the right thing because the API is expecting its messages to be logged, not displayed as the current status. So if you can build these strong abstractions, well-defined abstractions, this is what this type is for, then you can build really powerful hierarchies and get something that's maintainable and will work for you for many years and can be used in interesting ways, as long as you define those abstractions clearly and you can build on those. So this is something that that Scott talked about in Effective C++, which is to make sure public inheritance models IS-A. And the way that Andre and Herb said, public inheritance is substitutability. Inherit not to reuse, but to be reused. So again, the idea is to think about base classes as defining a generic type and then derive classes as implementing that type and making them substitutable for the type, not changing the meaning of what that type is, even if it's consistent with the API. So the next best practice guideline is one from Scott. He talks about this in More Effective C++, and I'm sorry, in Effective C++, he says, make non-leaf classes, it is more, I misspoke, it's More Effective C++. He says, make non-leaf classes abstract. Now, the reason he talked about this is because he identified a certain issue with object-oriented programming and wanted to address that and said, how can we make this issue, which is a potential gotcha, how can we make this safe? The interesting thing is, I'm not much concerned about the particular gotcha he pointed out, and we'll discuss why. But what I love is that if we follow this guideline, we actually make better hierarchies. And the quality of the hierarchy is an output of a design guideline that makes this a very attractive guideline for me. So here was the situation that Scott looked at and said, here's our problem. In object-oriented programming, we have derived class objects that we're referring to by base class pointers. So we have a couple of lizards here, but we're keeping track of them by pointers that are just pointers to the base class, pointers to animals. And Scott pointed out, we might see some code like this. So what are we doing here? Well, we are trying to assign the animal that's pointed to by p_animal2 into the animal that is pointed to by p_animal1. And code like this is not uncommon in C in order to, copy characters within strings or things like that. So this doesn't necessarily look like bad code, but is this going to do what we expect? Well, what is this code actually going to do? The compiler is going to look at this and saying, you're dereferencing p_animal2. What is that? That's a pointer to the animal. So the compiler thinks that what we have here is an animal. You and I know better. We're looking at the code and saying, no, what we have here, by dereferencing this, it's really a lizard. But the compiler thinks it's an animal. So what it's going to do is it's going to try to do an assignment of an animal to an animal, even though we're not looking at animals, we're looking at lizards. And so what we're going to get is slicing. In other words, the animal portion of the lizard, lizard2, is going to be copied over the animal portion of lizard1. That is almost certainly not what the caller was expecting to happen. It's not going to be a pleasant thing. And this code would actually compile even if the two animals at runtime are not even lizards. So it's possible that you might have an object that has a lot of data members in the derived class that exceed the size of the data members in the animal 2 might require more memory than the animal 1 has. So you might even be overwriting memory to do this. So it's slicing, it's dangerous, and it's not going to work the way we would expect it to work. So Scott's challenge was, how do we fix this? How do we make this so we can't have this particular problem? Now, the reason I'm not too upset about this is because I notice, we have this problem in a lot of potential situations. So for example, suppose I wrote this. I want to calculate the size of the animal pointed to by p_animal1. Is this going to do that? No, that's not going to work, right? Because what's this actually going to determine? This is not going to determine the size of lizard, which is what p_animal1 is pointing to. The compiler is going to look at this and say, oh, you're dereferencing a pointer to an animal. So what we get is an animal. What's the size of the animal? So this doesn't work. And in fact, we do this all the time in object-oriented programming. That's not going to be slicing, but it's still a logic error. Because in object-oriented programming, we're constantly lying to the compiler about our object pointers. We're always saying this is a base class pointer or this is a base class reference, but we know better. It's not actually that at runtime. The dynamic type is actually different. But this works fine. And the reason it works is because in object-oriented programming, we follow this rule. We only reference an object-oriented pointer reference to access base class members. We never make the assumption that we're actually pointing to an object of that type. Because most of the time we won't be. We'll be pointing to an object of derived type. But we still dereference it. Why do we dereference it and how do we dereference it? We dereference it to access, generally speaking, virtual functions, but anything that's in the base class we can do. And this is safe as long as we do this all the time. And that is what the example that Scott had isolated, that's what is not being done there. Dereferencing a pointer to a base class and treating it as if that's actually what we're looking at is a bug. It's a logic error, even if we could do what Scott wants to do, which is to make that not work. But so here's Scott's solution. Scott says we're going to make non-leaf classes abstract, and this solves the problem. But I'm not too worried about the problem Scott addressed. That's a more general problem that it doesn't solve in a really general way. But what I like about it is if you follow this advice, you're going to have better hierarchies. You're going to have more maintainable code. You're going to have things that are easier to reason about. So to implement Scott's solution to this problem, step one is make every class in your hierarchy either a base only or a leaf, a concrete class, a class that's actually going to be instantiated. So every class in your hierarchy is either something that's derived from or something that's instantiated. Now, in your typical situation, that's not an issue. because here we have a base class and we have 3 concrete classes that derive from it. Everything's good. But what happens is somebody comes along and says, oh, wait. We need another derived class. We need one, and it's going to work exactly like D2, but it's got one little tiny change. And this is what you're going to want to do. And I know this because I've wanted to do it and I have done it. And I've learned that it's a mistake. What you do is you say, oh, well, I'll just derive from D2. A new class is D3. It's derived from D2 because the behavior is almost exactly the same, but there's one little tweak, and we'll put that in D3, and now everybody's happy. And look how easy it was. I'm so quick. I can churn out code really easily and really quickly. This is not going to end well, and here's why. What's going to happen is over time, you're going to get new requirements. D2 is now going to have some slightly different behavior. But we don't want to have changes to D2 affect some other class that's not D2. But that's exactly what's going to happen. And so we now have this divergence between what we want D2 to do and D3 to do. Because initially, the definition of D3 was exactly like D2, except this little change. But now we want D2 to have some other behavior. And we end up, believe me, I've done this, where you try to write the code for D2 in such a way that it behaves properly when it's actually a D2, but also behaves properly when it's being derived from by D3. You can make this work. The code will be ugly. It will be hard to understand. It will be buggy, and it will be really hard to maintain. But this is the price we pay because it was so easy to make this change up front. This is not the way to do this. In fact, it violates one of Herb and Andre's most basic assumptions or guidelines, which is to give one entity one cohesive responsibility. Our problem here is that D2, which is one entity, but it has 2 responsibilities. One responsibility is to provide a concrete class for D2, but it has another responsibility to be the base class of D3. And so it has 2 responsibilities. And they might initially look like, oh, one class can do both. Over time, we're going to have more and more differentiation. So I have a question. And Popple says, does Scott's advice basically mean we want to have shallow hierarchies? No. And I'll show you right now the way this should actually be implemented. So the way it should be implemented is to separate out to refactor and create a new base class, and it has whatever's common to D2 and D3. Now, this has a single responsibility, which is to implement whatever's common between these 2 classes. Over time, now D2 and D3 can be maintained independently. No change to D2 is going to change D3 and vice versa. And over time, we might have a more and more complicated structure. It could be less and less shallow over time. But the important point to understand is that what Scott's saying is the leaf classes, all of these Ds, they are always concrete and never derived from. And then the base classes, the ones that are derived from, they are never concrete and they are never implemented. I hope this answers the question. There's no particular requirement that classes, that hierarchies be shallow. But there is a requirement that we don't do both with any one class. We don't make it a base class that can be derived from, but also a concrete class that's instantiated. All right. And this is robust in the face of maintenance because, as I said, D2 and D3 can be maintained independently, and no change made to D2 will affect D3 and vice versa. So following on, the first step, and that's actually the hardest step, is to make your hierarchies made up entirely of either bases or concrete classes. Once you've done that, then you go to the base and you make it abstract. And the way you do that is to add one or more pure virtual functions. And I'm not really going to get into the pure virtual function and what that means, but that's easy to look up. So you make absolutely certain that anything that is going to be derived from has at least one pure virtual function, and that guarantees the compiler will not allow it to be instantiated. Then, in order to address Scott's issue, you make the assignment operators protected. So thinking back to that assignment that we had, if the assignment operators for the base class, for the animal class, was protected, then trying to assign 2 animals to each other through base class pointers would not compile. And so we wouldn't have that particular problem. So that solves Scott's problem right there. Then the next thing we want to do is we want to go to our leaf classes. These are the classes that will actually be instantiated. So we make them concrete, and the way we do that is we override all pure virtual functions so they can be instantiated. Then you make their assignment operators public. And the reason we want to do that is because if you know that you're dealing with two lizards, you would like to make the assignment on the lizards themselves. You just don't do it through base class pointers. And so these assignment operators, and I say plural because of course you have move assignment and copy assignment, and you can do them both. And then you want to make this leaf class final, because remember what Scott said is you want to make your concrete classes not derived from. And so this was not something that Scott put, I added that. And the reason is that when Scott wrote effective C++, final was not in the standard. Final was introduced with C++11, and effective C++ is for classic C++. So this solves the slicing problem because we have protected the assignment operators on the base class. But I think what's more important is it makes for better hierarchies, more maintainable hierarchies. All right. Should you not also protect the move constructor, since this has the capability, the capacity to mutate? Well, because it's a constructor, it's never referenced by base class pointer. So I don't think constructors are the issue here. All right. Follow-up question. Does it mean that we don't want to cast base classes in stone and never change them, but rather change the hierarchies in response to changes of leaf types? Well, ideally, yes. We want to embrace the model that says we want to be able to extend without modifying. And object-oriented programming does that very well. But there are times when we'll want to revisit something. So consider the case where we had we wanted to introduce a D3, and we wanted to be similar to D2. If we can modify D2, if you have source, then you can make the refactoring that we discussed. If not, then you're actually going to have to duplicate the code. If you really say, well, we can't modify D2. So you can do this kind of extend but don't modify. Although if you own the code, you're going to be doing refactorings and modifications all the time. So, but it's not necessary. Is there any guideline requiring member variables inside base classes? Oh, regarding member variables inside base classes. In general, there's kind of a bit of a frowning on this, but I don't have any guideline that touches on it. I think if it's done in support of something that's clearly going to be needed, then it makes sense. The thing is, you're already, when you start to put data members in bases, you're starting to think about how this is implemented, and that really shouldn't be the key requirement of the base class. So in general, data members of base classes, it's not a huge design smell, but I would kind of question it. All right, so the last guideline I'm going to do from a design point of view is to talk about, is to talk about using the non-virtual interface idiom. And this is something that Scott refers to. I don't know that he refers to it by name, but in Effective C++, item 35, he says, consider alternatives to virtual functions. And if you read that item, you'll see how that makes sense with the non-virtual interface. But Herb and Andre go into more detail about it, and they say in item 39, consider making virtual functions non-public and public functions non-virtual. So what are we talking about here? So let's go back to our example. Here is how we implemented Logger, and this is how a lot of people would have implemented it. But in the NVI approach, which is a little worrier, it was implemented this way. And so what are we doing that's different here? Well, the public interface to do the log message is no longer virtual. Instead, we have introduced a private, could also be protected as long as it's not public. We've introduced a private member function that is virtual, that is the function that log message is going to call that can be overridden. So one of the advantages of this is that we can, so the definition of the NVI is that the public API is non-virtual. It calls non-public virtuals to do the work. And I will point out that destructors are specifically called out as an exception to this. Go ahead and make the destructors public. That's not an issue. Make them virtual and make them public. And part of the value of this is that we now can do whatever pre and post functionality that we want to do. Notice if you allow clients to directly call into the virtual function, then the base class object has no ability to do any kind of pre-processing or post-processing or anything like that. It has given away direct access to the derived, directly to the overridden functions. So in the NVI, the base class is in control. It can enforce pre and post conditions. If you're wanting to do instrumentation, if you want to set debug points, then you have something to do that. But also understand it's very, very robust in the face of changes. If you don't use the NVI idiom and then you later decide there's something we have to do before every call to one of our virtual functions, there's no way to add any pre or post functions without breaking the callers or derivers. You're either going to break the callers or the derivers or perhaps both in order to make this happen. Now, if you say, well, I own the whole code base, I'm not actually selling my framework to some third party or to some clients, and so I own all of the code. If I want to make a change, I can make the change. But this actually is more robust in face of changes. But that's not the real power. The real power is that it allows each interface to take its natural shape. Now, what do I mean by that? And by the way, I'll point out that Scott didn't really talk about this part. He got this part, and if you read the item that I referenced, you'll understand what he was talking about there. But I think this is the most important part, and this is what's explained in Herb and Andre's book, that each interface can take its natural shape. Now, what do I mean by that? Well, there's actually two interfaces that are going on here. One is the interface to the client, the callers. Anything that's public is an interface to the callers. But we also have the interface for implementers. And anything that's virtual is part of the interface to implementers. If you make your functions both public and virtual, then you're overlapping the two interfaces. You're saying that I can write a function that's going to be optimized for both interfaces. And that's possible, but it doesn't necessarily seem likely. It violates, again, this very important guideline to give one entity one cohesive responsibility. Here we have a function, and we're saying this function is going to be part of the public API, so the callers can call it, but it's also going to be part of the derived API, so derivers can derive from it or override it. And there's not any particular reason to assume that what's optimal for one is optimal for the other. In other words, the two interfaces not necessarily going to overlap cleanly. So I suspect there's people in the audience who are feeling the way that I felt when I read this from Scott and Andre, or from Herb and Andre, and it was like, well, it seems to have a lot of boilerplate to it. There's this function that turns around and just calls another function. I'm not sure, but I kind of see the advantage. So I decided, well, I'll give it a try for a while. I'll play with this. And the hierarchy that I was working on at the time, I happened to be working on a base class and derived classes in order to solve a particular problem. So I said, well, I'll apply this here. And that first implementation, when I first made this change to use the NVI, one of the things I noticed immediately was that in this particular situation, my base class had 3 different virtual functions. There were 3 different ways I wanted to be able to allow derived classes to override the behavior. But as I created the non-virtual public calls, one of the things I realized was that for callers, there was no use case which didn't involve calling two of the three functions one right after the other. In other words, from the caller's point of view, there really only needed to be two functions. One of them was going to call into a virtual, but the other function was going to call two virtuals. And they needed to be separate because I wanted the derived classes to be able to override them independently. But from the caller's point of view, they didn't need to be two. From the caller's point of view, having to call these two virtual functions would always have been call this function and then immediately call this function. It was a complete waste. It wasn't optimizing the two different interfaces. And so that's what's made me be a huge believer in the NVI, because now I understand very clearly what we're talking about when we say the interfaces, what you want to optimize for callers and what you want to optimize for derived classes are not necessarily going to be the same thing. And in my experience, are very often not the same thing. Consider you might, for example, have data types that the derived classes know about that clients don't need to know about. You might have, for example, the derived types, you might want to return an error message that is not the exact error or error type, that is not the exact error type you want returned to callers. You might want to grab that error type, change it into some other mapping. There's a number of reasons why you might want to have the derived classes throw exceptions, but you might want to return error codes to the callers. There's a number of reasons why you might not want to have the exact same API. And if you start out knowing I'm going to define these two APIs differently, you'll find, I think, that it's very, very common that you don't want to have the exact same API. And the NVI will, again, have you build more usable and more maintainable hierarchies. So these are the three design level guidelines that I would give. Use object-oriented programming to model is a relationships, not for code reuse. Make your non-leaf classes abstract, and your leaf classes, your concrete classes, not derived from. And then use the non-virtual interface idiom. Again, the reason we do this, the strong reason to do this, is not just that it makes the classes a little more robust in the face of change, but because it allows you to optimize the two interfaces separately. All right, so let's now talk about some build level or code level optimizations, or best practices. I shouldn't say optimization, best practices. And one of the things I'm going to say is that you're going to find out that in the slides I'm going to show you, I'm not going to use the NVI idiom because that makes the slide a little bit more crowded. This is not because I don't believe strongly in the NVI idiom. I do. It is what I follow consistently, but you're not going to see it in these slides because there is a little bit more boilerplate. It takes up a little more space in the slides. So consider that as we talk about the build practices. All right, so I want to introduce Chris. So Chris is using a legacy framework. Chris doesn't have write access to the framework's code. Chris is just writing client code. And they discover an error in a base class, but it's in a non-virtual function. Excuse me, there's a question here. Isn't making non-public virtual functions defeating the aim of having one base class and only one implemented class? Isn't making, I don't see that. And I'm not even sure that's our aim, is to have only one implementing class. I don't know why we would want, I mean, you can have multiple implementing classes. I'm not sure I'm getting the question. I don't think that having non-public virtual functions does that. Send me a text or an email elaborating on what the question is, and maybe we can drill into that a little better. Okay? All right. So getting back to Chris, they discover there's an error in a base class, but in a non-virtual function. So it wasn't designed to be overridden, but Chris is desperate for a solution. So they write an override function, even though the base function isn't virtual. But because Chris isn't certain if this is going to work, because we've been told that you only override virtual functions, they write a test function. So here's what we've got. Here's the base, and in this function, which is very fortunately called erroneous to indicate that there's a problem here. The erroneous returns 0, but really, Chris feels like erroneous should really return 1. So erroneous overrides or attempts to override erroneous because erroneous isn't virtual. So can we override it? I don't know. So then Chris wrote a function called test erroneous. And what it does is it calls erroneous and verifies that it actually returns the value we're expecting instead of the wrong value. And then if that happens, we'll output success. So in our main, then we create an object of this derived class, and then we call test erroneous. So the first question is, will this test pass? So I want to see a show of hands. Do you think this test is going to pass? I'm not seeing any hands yet, but I saw some hands going up. Okay, not seeing a lot of hands. I guess people don't think this test is going to pass. Oh, there's one more hand. A few more hands. Okay, so is the test going to pass? Well, I think it is going to pass. The test is going to pass, but that's not the real question we want. The real question we want to ask is the fix successful? Now, why would the test pass if the fix isn't successful? Or I should say, why would we ask? If the test passed, doesn't that mean the fix is successful? Isn't this telling us that the fix is successful? Well, so put your hands up if you think the fix is successful. I see fewer hands now, so I think people figured that out. So put their hands down if they don't think the fix is successful. So what's going on here? Okay, well, we have created this object here, and then we call test erroneous. Test erroneous now is going to call erroneous. Now, which erroneous is it going to call? Is it going to call this one or is it going to call this one? Well, it's calling erroneous based on this and the this function or the this type, which is derived. So it's calling derived : erroneous. It's calling it on this. And so it's going to call this. It's in the scope here. It's not virtual. So it's not going to, if there was a further derived class, it wouldn't call that one. But we were within the scope of derived. And so when we call erroneous, it's going to get this erroneous. And so it's going to get the correct function. But the fix is not successful because this isn't going to work. And why is it not going to work? Well, here's the problem. Remember, the way that we write object-oriented code is that we always refer to objects by base class pointers. So the way that the testing should have been done is to have written code like this. So here what we're doing is we are creating an object, but we're referencing it with a base class pointer. And then we use the base class pointer to call erroneous. And now what's going to happen? Well, what's going to happen is that that's going to call this erroneous because there is no virtual function here. So it's not going to call the derived erroneous, it's going to call this one. So Chris's solution is only going to work in a non-object oriented way. In other words, if we actually know the object is the derived class, then we can just, but notice it doesn't even have to be the same name. You just have to call the right function. So this isn't going to work. Is this test going to pass? No, this test will not pass because this fix is not the successful fix. I hope that's clear. I'm going to jump back over to Q&A. Looks like we have another question here. This or this is unclear. We can't see what you point to. Oh, I'm sorry. I thought you could see my pointer here. Okay, I'll try to be a little more clear on that. I apologize. Sorry about that. Okay, so the next thing I want to emphasize for you is to always make base class destructors virtual. So, overridden functions must be declared virtual. We aren't going to be able to see your. We aren't going to be able to override things that are not virtual. If you want to override, it has to be of a virtual function, or that's just not going to work. The next guideline is always make base class destructors virtual. All right, so here is a rewrite of our logger example. And in this logger example, I have removed the destructor, virtual destructor. Do not do this. Do not do this. Okay, sounds like I can use a pointer. Okay, great, thanks. So don't do this. But let's take a look at what would happen if we did this. So here we have the file logger, and the file logger has one of its data members is it makes a stream, right? Okay, so let's look at how this could be used in client code. And here we are in main. Main creates a file logger, but it refers to it with a base class pointer, not a file logger pointer. And so when we get down here and we are going to delete this, then which destructor is going to be called? Well, because it's not virtual, it's not going to get the most derived destructor. Instead, it's going to call the destructor of the base class, right? And that means that the data members that are in file logger are never going to be cleaned up, because that object is going to have the memory is going to be lost, but there's no calling of the destructor of the stream. It's not going to clean up the stream, so we're not going to be happy about that. Notice, even if file logger didn't happen to have any data members, the standard says that deleting a derived class through a base class pointer that doesn't have a virtual destructor is undefined behavior. So you could imagine a world in which if there was no data members in the derived class, this would actually be okay. It would work okay, but you have no guarantees. The standard says that's undefined behavior. So we want to stay away from that. So our guideline then is always make base class destructors virtual, and Scott has put this in Effective C++, and Herb and Andre included as one of their guidelines to make base class destructors public and virtual, or protected and non-virtual. So there is a case, and you can read item 50 about a situation where you have non-public destructors and you don't need to be virtual in that case, but that's kind of a specialized case. So in general, we want to make sure that if we have any virtual functions, that the destructor is one of the virtual functions. All right, so here's another example, and this is our console logging example. And when I write the console logging example, I recommend that virtual functions always be labeled virtual, but that's actually optional. If we override a virtual function, then the compiler is going to make that virtual. Notice I have some pushback from people who say, wait a minute, this is already has the keyword, or the contextual keyword override is here already. That makes the virtual keyword redundant. Totally agree. Virtual is just redundant, but I'm happy with it. I recommend that we use it, even though, given that we have override here, that is redundant, but I like it because I like to be able to look at functions and know whether or not they're virtual. And so it's not telling me anything in the compiler, but it's telling something to me, telling me this is virtual. Now I have, in this particular override, I have removed the virtual for log message, and also I've removed the override. So it doesn't say virtual, doesn't say override. And the question is this log message still virtual? So let's see a show of hands. If you still think that I don't need override, or I don't need override and I don't need virtual, is this still going to be virtual? Not seeing very many hands. I see one hand. All right, so most people think that this is not going to be, oh, now I'm seeing a bunch of hands. Okay, so some people, at least, the people who, I'm not seeing everybody's hands. So that means either people aren't voting or they don't think it will be virtual, but I am seeing a bunch of hands. And for those of you, then, oh, Dwight says no, it's false. It's not going to be virtual. Why not? Well, the reason is that it's not virtual because the signatures don't match exactly. So while you weren't looking, I took out the const. So yeah, I played a mean trick on you, but there's a point to playing the mean trick. It wasn't just to be mean. The reason I pointed this out is that it's very easy to overlook the fact that this is not an exact match of signatures. If we put in the override, if we put the keyword override back in, then what you see is that we would get an error. The override is going to catch the problem that we, as humans looking at this, we missed, which is the signature is not exact. it's very, very easy to drop a const. It's very easy to have a long instead of an int or something like that. If the signature is not exact, it's not going to be an override. And so I'm looking at this code and I'm saying, oh, there's log message. It's going to override. It's a virtual function that's going to override. And in fact, it's not. So that's why the override keyword can catch problems like this. So override actually does two things for us. It communicates our intent to people reading the code. Oh, this function is an override, but it also is verified by the compiler. So in the previous example, if the signatures aren't perfect matches, and as I said, that's really easy to have happen, then we'll still catch it. The compiler will catch it and say, no, 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 you think that's an override, but you're wrong. And then I look at it and I say, oh, not a perfect match of signature. That's why. All right, so so the guideline here, and this is, of course, override was not introduced to C++11, so we see it in Scott's modern C++, the one that's not published by Addison Wesley. The modern C++ has as item 12, declare your override functions override. So I want to look at one other thing now. We're going to talk about scope. Now, in C++, it is perfectly legal to define an identifier that has already been defined if you define it in a smaller scope, in an inner scope, right? So we've defined X previously, and now inside an inner scope, we define X again. So what is an inner scope? Well, it could be a nested namespace. It could be a function within a namespace. There's a number of different ways that you can have a nested scope. And this is actually true even if the two objects are different. So for example, the X here in the out scope could be a type, and the X in the inner scope could be a variable name. So that is perfectly legal C++. It may be confusing, and the way C++ code works is that once you've introduced this new thing, the code sees the new thing and it hides the old thing. So I gave you some examples of scopes. A scope can be a type inside a namespace or inside another type, or one of the things that also can be is that a derived type is considered inner to its base. And at first that might seem weird, but if you think about it, you do want any code in a derived type to be able to see everything in its base. And so that means that it's treated as an inner scope to the base. So any derived class declaration will hide the base declaration of the same name. So here's an example. And in this case, in the base class, I have declared that X is an alias for the class int. And then in the derived class, I declare that X is actually an instance int. And then I try to make a vector of X. Well, if X was an int, then you could have a vector of int. But it doesn't make sense to have a vector of a particular member. Does everybody follow that? So this isn't going to compile because although we did to say that base : X is a type alias, and so you could have a vector of base : X, but you can't have a vector of derived : X. And at this point, that's what we're going to see. The derived : X is hiding base : X. So the compiler doesn't see that it's a type, it sees it as a data member, okay? So when this gets really interesting is when we start talking about functions. So the reason it's interesting is because unlike other types, we actually can have multiple functions that have the exact same name. So if for example, if you define a type foo, you can't come along later and define in the same scope. You can't define a new type foo. You could in an inner scope, as I said, that hides the outer foo, but you couldn't do it in an inner scope. But for a function, you can have a function foo and then create another function foo. As long as the signatures are different, you can keep creating functions with the same name all day long. So when we are looking for the function, when we call a function, what the rules are is that you look for the called name in a particular scope. If you find it in that scope, you collect all the candidates in the scope. That's how we do overloading. If you define I'm going to call foo on this. Then the compiler goes and looks in the scope for all foos, not just one foo. It doesn't stop when it finds a foo. It has to find all foos in the scope. However, it doesn't look any further once it finds any foos in a scope. It doesn't look at any other scopes. If it doesn't find anything in the scope, then it goes to the next outer scope and then repeats. So what we're going to do is we're going to look in increasingly outer scopes until we find one instance of the called name, and then we're going to find all the instances in that scope and stop looking. So what this means is that overloading doesn't happen across scopes. Now, I would point out this is kind of simplified. When you get into ADL and using declarations and things like that, you can actually overload it across scopes, but we're right now going to ignore that because it's not important for the particular point I'm making here. So here is our base, and in our base we have defined a function called foo, which takes an int, and then in the derived class we defined a function foo which takes a long, and a function foo which takes double. So now in the constructor I'm going to call foo with a long, foo with a double, and then foo with an int. Pretty follow what we're doing? I asked this question and I can't really hear if you're answering or not, but that's what we're doing. So the question is, what is the output of a call to the derives default constructor? So here's our default constructor, and we're going to call foo with a long. Put up your hand if you believe that this is going to call this function. Am I seeing any hands go up? No hands yet. You guys are really skeptical. You think I'm going to try to fool you again. No hands. Oh, I'm seeing hands. Okay, sorry, I was looking in the wrong place. So we have a bunch of hands coming up, and you're right. That's exactly what's going to happen. We're going to output 1 on this line. And when we get to this line, we're going to call double. So everybody, leave your hand up if you think that you're going to return 2 here. Still have a bunch of hands up. Okay. Now we get here now. Now we're calling foo with an int. Now the question is, put your hands up if you think we're going to call base. So leave your hands up if you think we're going to call base. Otherwise, put your hands down. Okay, I'm seeing hands go down, right? So put your hand down if you think that we are going to call this because this is hidden, right? Your hands are down. That means that we're going to call this instead of this. And so what does Dwight say? Dwight says false. Of course, again, I set you up because I only gave you 2 choices, only hands up and hands down. The problem is neither of these is going to happen. We're not going to print out 0. We're not going to print out 1. Why? Well, the call is ambiguous. In other words, calling with an int, it's not clear from the compiler's point of view, do you want the long or do you want the double? It could be converted either way. So there's no right answer here. I set you up. Looks like we have a question. Let's look at the question. Pointer is gone. My fault. Sorry about that. Okay, so my point, the overall point, despite all the tricky stuff I was throwing at you, the overall point is that by introducing foo in the derived class, we hid it in the base class. Now we have a question. What if foo was virtual, right? If this is virtual, then we would expect to be able to have that work in both the base and the derived class. Isn't that what virtual means? And it turns out, no, this changes nothing. Why? Because these signatures aren't perfect match. So this virtual is not overriding this. It's an attempt to overload it. In other words, we're trying to make virtual that has a different signature. And that is not going to succeed. Why? Because as I said earlier, you don't overload across scopes. You only overload within a scope. So this is going to come up when coders try to try to overload virtual functions. That's not going to work. Don't do this. If you actually are trying to overload or override, then use the override keyword and you'll be guaranteed it's overriding. If not, if you're trying to overload, just know that's probably not going to work. It's technically possible by using stuff, and it can be done, but it's probably not going to make you happy because it's probably not what you want to do. So don't mix overloading and overriding, or as Scott says in item 33, avoid hiding inherited names. All right, so let's talk about default parameter values. So here's Chris again. Chris is, again, using this legacy framework, can't change the framework code. They override a virtual function, and the virtual function has a default parameter, but Chris thinks the default parameter is a bad default. So they change it in the overriding declaration. But Chris isn't certain, is this going to work or not? So they write a test function in the derived class. So here we have a base, and we have this function which is handily called bad default, and the default there is 0. So Chris overrides this, and in Chris's bad default, we say, oh, I want the default to be 1 instead of 0, and then I'm going to test it. So I test it by calling, by making certain that when we call bad default, we get 1 instead of 0, and then we test it by saying, here is we call test bad default, and now the question is this test going to pass? So put your hand up if you think this test is going to pass. All right, there's one hand. Not seeing a lot of hands, but seeing a few hands. What's going to happen when we call this test? Well, what's going to happen is that we call test bad default. Test bad default is going to call bad default, and the bad default is going to call the one that is defined in this class. So it's going to get this definition. So the test is going to pass. But now the question is the fix successful? So put your hand down if you think the fix is not successful. Put your hand up or leave it up if you think the fix is successful. Is this going to work the way we want it to work? All right, people have caught on to my little game here. The hands are going down. Why is it not going to work? Well, the reason is the way this test should have been written is this way. Again, we are using object-oriented programming, so the way to test it is to test it the way object-oriented programming is written, which is to say we're going to create an object of the derived class and reference it with a base class pointer. Now, notice when this code is compiled, the compiler doesn't know the type that B is pointing to. It's a base class pointer. So the compiler looks at the interface of what we're trying to do. It's bad default. It looks up here. It says, what is the default? Because no parameters provided. So it has to look at what the default is, and it uses this 0. And it does not matter what is actually being pointed to here. It's going to use the base class definition, and that's just what it's going to use. And so if we write the code the way it will be used in practice, we would recognize that we are not going to get this signature seen by the compiler at compile time. At compile time, the compiler is only going to look at the base class pointer, and it's going to see this signature, and it's going to use this default value. So this is not going to work. All right, we have a question. Let's take a look at the question. Could you explain the difference between override and overload? Sorry about that. So override is what we've been talking about in terms of virtual functions. If we have a virtual function and in a derived class we redefine the implementation of the virtual function, that is called an override. An overload is when we have the same function name with different signatures. Okay, so in other words, if I want to have like absolute value, and I want to write one version that takes an int and another version that takes float. So I have two different versions with the exact same name, absolute value. But I've written two implementation, one that takes an int, one that takes a float. Those are overloads. But in the examples that we've been talking about for hierarchy, where we use overriding, that's the exact same signature in a derived class, and that's an override. And mixing those, not going to make us happy. If we're using NVI, is this really an issue? Are we talking about for overload versus override? Probably not if you're using NVI. That would probably sidestep the whole problem. Could you explain the difference between override and overload? I missed that. Oh, I think I did that one. I guess I got these questions out of order. Overloading a method or function in C++ is the ability Is somebody answering the question? I think that's what's happening here. You're trying to answer the question of what's the difference? All right. I think that is an answer to the question of what's the difference between overwriting and overloading. Okay. So now, when writing this code here, one of the things that someone might have looked at and said, oh, you're overwriting bad default, which has a default value of 0. If you don't have the same value, you're going to confuse people. So I should probably write my default value also to be 0. And in my opinion, that's a mistake. And the reason it's a mistake is because it's going to work fine as long as the base class default value is never changed. But if through maintenance or for whatever reason, if we ever change the base class default value of what it's of, if we ever change the default of the base class, and you still have here, if you've changed this to be 0, and then in some future revision, we've changed this base class value, then again, we've fallen into this trap of people looking at this and not understanding what the true default is going to be. So the real answer here, what Scott advises, Scott advises that you don't make any default parameters at all. Specifying the default parameter, this is what I was getting at. You actually have kind of a DRY violation. You've put the same default parameter in both places. If the base class is ever changed, then you're going to be out of sync, and we don't want to do that. So Scott's advice is never refine a function's inherited default parameter. Just leave default parameters alone. That's the problem of the base class. For the NVI question, I meant the default value. The default value would be in the non-virtual function for the caller. The virtual functions would not have a, okay, yes, you're absolutely right. It's not going to really be an issue. And in fact, yeah, you don't want to specify any default value for overriding functions. You still don't want to. It's probably not going to be a problem because the base class is what's going to call the derived. Although in NVI, it's possible for the derived functions to be protected instead of public or instead of private. And that means that a derived class could call another derived class function. And if it was of a different type, you could run into the same problem. It's not as likely to be an issue. Is Chris fixing things badly or testing things badly or both? Well, Chris is definitely testing things badly. But the real problem is what Chris is trying to do is just things that can't be done. And I wanted to demonstrate that why it's not done. So that's why I wanted to show what would happen if you tried to do it. It might look like it's going to work, but it's actually not going to work. So Chris is definitely testing things badly, but Chris is in a hard place because Chris is trying to fix things that can't be fixed without modifying the base class. And that's kind of part of what I was trying to point out. All right, so we have one last example. I'm running a little short of time. So in this last example, what we're doing is I want to, when I'm creating my logger, in the base class, in the logger itself, I want to log that we've created the logger, right? So we create the logger, and in the constructor of logger, we're going to call the log message, right? This sounds good. Now we know that the logger has been created, but there's a problem here. And the problem is that the constructor is actually calling a virtual function. And the problem here is that when we are constructing our file logger, which constructor is going to be called first? Well, it's going to call the logger's constructor. And after that's completed, then it's going to call the file logger's constructor, right? We construct the base classes first, and then we construct derived classes. So this constructor is going to be called before the file logger constructor. Now, the problem is that the file logger constructor is what actually opens the file. So if you call log message, it's going to try to log this string to a file that's not open. I hope you see the problem with that, right? Okay, so when a types constructor or destructor is executing, the static and dynamic type of the object is that type. So understand, when we're calling the base class constructor, the type of that object is that base class, even if eventually it's going to be a derived class. But the type, according to the language, is the base class's type. So this is true even if the object being constructed is eventually going to be a derived type. So that means that the virtual functions will not resolve to a function in the derived type during construction or destruction. We don't want that. The reason we don't want that, this is a good thing. Even though it sounds like, well, that's really annoying. I would like to be able to call virtual functions in my constructor. But the problem is, if you did, we would have the problem that we just outlined with file logger, which is that you're trying to write to a file that hasn't been opened yet because the file logger's constructor hasn't been called yet. So the way around that is that the language just says, when you're in the constructor of some type and you call a virtual function, we're going to get that type. It's not going to be treated as virtual. It's not going to go up the hierarchy. It's going to get the function that's at that level. And this is frustrating for people, but you need to understand this is the right thing to do. Because as I said, in the file logger case, a call to log message in the base class would try to write to a file stream that's not been initialized. So we don't want that. So don't call virtual functions in constructors or destructors. So we've got one last thing I want to point out. Now here's a situation where in our logging, we actually have different people who might want to be notified about logging. So our logging process running on our server interacts with inventory, interacts with production process, interacts with maybe even corporate legal and things like that. And so when we're logging things, we might want to have an SMS logger, which actually pages people for certain kinds of logging, but we need to know who we want to page. Do we want to page production control? Do we want to page legal? Do we want to page accounting? Do we want to page inventory control? Who do we want to page? And so what we did is, in our SMS logger, what we have is we want to set the phone number for the callee, so when we log that message, it actually calls them, right? But the problem is, in your app code, when you call logger set callee, it's not going to work. Why? Because what is logger? Logger, remember, is a base class pointer. And we've introduced this new set callee in the derived class. So logger doesn't know about set callee. It's not a virtual function. It's not an override. It's introduced here in SMS logger. So how do we deal with this? Well, one way to do this is to do a cast. So we can do a cast of our logger and say, no, you are an SMS logger. And if that's true, then that's going to set this. Is this going to work? Yes, it's going to work, and it's going to be really efficient too. It's going to compile. It's going to work. It's going to be really efficient. What is the problem? Well, the problem is, what if it's not actually, what if you're wrong? What if you're saying, I want to cast this logger to an SMS logger, and it's not an SMS logger? Maybe it's one of our different kinds of loggers. What's the problem? Well, I'm explaining upcasting versus downcasting, and because I'm out of time, I'm going to jump past that part and basically say that when we're doing upcasting, that's safe, but doing downcasting is not safe, and I'll let you read the slides later. But the point is that when we do if we do downcasting, one way to do it is what I just showed you, which is to do an unconditional static cast, which I just showed you. The problem is the compiler can't verify that it's right. It's going to be undefined behavior if it's wrong. And then even if it's right with the current code, it's possible that as you modify code, you break code in undefined behavior. It is effective and it's efficient. You can do it. It's legal, but it can be really dangerous. So there's another way of doing it, and that is with a dynamic cast. And the dynamic cast actually checks at runtime to see if the cast is going to be safe. And so there is a little bit of runtime overhead because we're doing a little bit of verification, and we have to code for the failure case. So let's take a look at this syntax. So here is our SMS logger. We're using a dynamic cast. So what happens is if the logger actually is an SMS logger, then this pointer is non-zero. So we have to do a null pointer check. If it's not zero, that means it really is an SMS pointer. It's safe to call to set the pager for it. But if it's not, then you have to deal with, well, what if it's not that? You have to deal with a failure case. Now, we can also do cast instead of the pointer. We could do a cast of a reference. Now, we don't have to check to see if the reference is zero because references are never zero. So it looks like this can't fail. Of course, it can fail. It's possible that logger is not an SMS logger. What would happen in that situation? So in this situation, when the dynamic cast fails, you end up with a null pointer. In the bottom situation, if it fails, you're going to throw an exception. So either way, you have to deal with the failure case. This is safe. There's a little bit of overhead to it because we are doing some checking, but it is safe. Now, I feel like there's actually a better option than doing the casting at all. And in the better option, the approach is rather than trying to cast is to rethink about the problem. And we can't always do this, but the idea is to try to express the problem in a way that makes sense for all objects, not just the ones that has some special behavior. So in this example, what I've done is I've gone back to logger and I said, look, as we are logging messages, one of the things you might want to do is you might want to set the department info of what is the department info that's interested in the logging messages that you're about to make. And so setting the department info may not actually have any side effect at all. It's a virtual function in the base class. It does nothing. So we write our client code setting the department info whenever we want to switch departments and say, I'm about to log some things that are of interest to the inventory department, or I'm about to log some things that are interested in process control. And then in the logger, there we are interested, because what we do is when you give us a department, we look up the on-call number and we call set callee for that particular department. So you see what I've done here is I have redefined the problem. I was saying the problem is that I want a phone number for SMS messages. But the truth is, what I really want to do is I simply want to tell the logger that a different department is interested in these log messages. And for some loggers, we don't need to know anything. We don't do anything with that information. But for some loggers, for example, the SMS logger, it's going to do something with that information. So I have redefined the problem. I've redefined the API so that all objects respond to the API I want, and then I just change my app code in the way I want. So you can't necessarily always do that, but if you can go back and redefine the base class, then you can incorporate whatever functionality you want by thinking of it logically. And instead of saying, well, this particular type has a particular requirement, so if it's that type, I want to do this, and say, no, what is the general problem here? And the general problem is some logging is of interest to different departments in this case. Okay. All right. So, so the recommendation here is to use dynamic cast rather than static cast because it's safer when you're doing downcasting. But a better solution is to avoid casting by refactoring, although refactoring is not always possible. So those are the build guidelines. Overridden functions must be declared virtual. Always make base class destructors virtual. This is for polymorphic base classes if you're doing object-oriented programming. I certainly don't want everybody to make all destructors virtual. That would be bad. Use override if you are overriding functions. This communicates something to readers, but also causes the compiler to verify that what we're doing is what we intend to be doing. Do not mix overloading and overriding, and we talked about the differences between overloading and overriding. Don't specify default values on overrides. The default value is determined by the base class, and that's just the way it's going to be. Don't call virtual functions in constructors or destructors. This is a little bit annoying, but it is the correct behavior, and it is what you have to do. And then, again, use dynamic rather than static casts for downcasting. A little bit of overhead, but safer. But even better is to refactor the problem so that you don't need to do casting at all. That's not always possible, but when it is possible, that's best. And as a review of the design guidelines, use the object-oriented programming model with is-a relationships, not just to avoid code duplication. Make non-leaf classes abstract. We talked about the problem that was trying to solve, but the overall improvement in hierarchies is the real win there. And then use the non-virtual interface idiom. This is a very valuable way of separating the interface, the calling interface, and the overriding interface so that you can write the best possible interface for those situations. So I went a little bit over time. I'm going to be hanging out in Remo, and I'm happy to take questions. I'll be at a table there. I'm not sure which table. I think I'm at table 2, but I'm happy to take questions, and I'll be hanging out for a while through the break. So thank you all very much for attending. I hope you got a lot out of it. Thanks.